Yeah, I'm going to talk about simulating the universe, but before I talk about how we do that, and then come on to that simulation hypothesis about whether we might even live already inside a simulation, I wanted to just give you a sense of scale of what it is that we are talking about, or what do we mean by the universe. So if you look at the stars, not these stars, those stars, or better yet, the real stars, if you go out and look into the sky, you'll just see a handful of them. If you allow your eyes to adjust, then very gradually you'll start to see more, maybe a few hundred. If you go somewhere with a really dark sky away from city lights, you might get to see a few thousands. And eventually, as your eyes adapt to the darkness, you start to see a milky band of light splitting the sky. And that's the Milky Way. That's the galaxy where we live. And what you're really seeing when you see that faint band of light is hundreds of billions of stars, just so distant that all you actually see is that band of light. They all kind of mash into one. But make no mistake, those stars are equivalent size, or some of them even bigger than our sun. And one of the most remarkable developments in astronomy in recent years has been the discovery that many, perhaps most, of those stars have planets around them as well. So there are hundreds of billions of stars, and they quite possibly all have planets around them. But when it comes to simulating the universe, that is still the tip of the iceberg. If you know where to look, on a really dark night, you can see a kind of smear of light. It doesn't quite look like this. This is what you get if you take it with a really great telescope. You can see a little smear of light in the sky, and that is called the Andromeda galaxy. That is another galaxy with its own hundreds of billions of stars far beyond our own. But actually, that is still just our cosmic doorstep. The Andromeda galaxy is like a twin to our Milky Way. It's relatively nearby. The rest of the universe has many more galaxies. If you know where to look, you can find them in a telescope. And in fact, if you're willing to drop about $10 billion, then you can have the James Webb Space Telescope. And this is a picture from JWST from just a few weeks ago, showing what JWST sees out in space when it points into a tiny patch of the sky. It's far smaller than the moon, this patch of the sky. It's around about a third of the diameter of the moon. And what you are seeing there is the result of taking the world's most powerful telescope, pointing it into that tiny patch of the sky, and everything you see there is another galaxy far beyond our own, each with their tens or hundreds of billions of stars. So if you extrapolate this, if you try and extrapolate this to the scale of how far we can see in the universe, there are likely to be trillions of galaxies observable to us in the universe. And there may be even stuff beyond that, we don't know. Now, this is quite a small patch of the universe that you're looking at here. If you can zoom out even further, then you'll find that the galaxies are not just dotted at random, as they appear to be here. In fact, galaxies are organized on mind-bogglingly large scales, scales that are hundreds of millions of light years across. And the organization, we think, looks somewhat like this. This is actually the first thing that you're seeing that's from a computer simulation of the universe, and I'll say a bit about how we make something like that in just a moment. But what you're seeing now is on such large scales that an individual galaxy is now just a dot. And you're seeing the individual galaxies now, with their hundreds of billions of stars, merging into kind of streaks of light. And it's forming this very distinctive geometry that we call the cosmic web. It's almost like a cobweb on these crazy large scales, with these kind of beads of light, like kind of dew glistening in the morning sun. And one of the fundamental questions that we have is, how did the universe get to be like this? How did it get to be so richly structured with all of these stars and planets, and you can go up to galaxies, and then the galaxies themselves are organized into this gigantic web? And in a sense, this is the fundamental question of cosmology. How did the universe get to be organized like this? Now, although that's a simulation, we are measuring this cosmic web. I'm not telling you stuff that's not true. We can actually measure this. If you've been watching the news, you might have seen that the Euclid telescope just launched into space just a few days ago. And that is a very different type of telescope from the James Webb telescope. It's specifically designed to scan across the whole sky and build up a picture of this cosmic web. So rather than focusing in on individuals or small patches of the universe, it's going to give us a snapshot of the universe as a whole. But when we've done that so far, one of the things that we've learned is that actually what you're seeing here is still the tip of the iceberg in some sense. Because everything that I've shown you so far, in fact, makes up just 5% of what we think is out there in the universe. It is our understanding that 95% of the universe is actually completely invisible to our telescopes, because it's made out of materials that don't interact directly with light. We call them dark matter and dark energy. It doesn't, the name is not great, to be honest, because these things are not dark in the sense that they don't absorb light, they don't create shadows. Rather, they're transparent, so you can't see them directly. And no, we don't know what they are, but the idea of there being materials out there that are transparent is quite a comfortable one for physicists. We know that there are many particles that we can, experiment with in laboratories that are very hard to detect through their light. So in terms of the physics of this, it's not a huge problem, but it does mean it's very, very hard to tell what's really going on with those materials. And this is where the adventure into computer simulation really starts. In a computer simulation, what we do is program a computer with what we believe to be the laws of physics. So that would be things like Einstein's general relativity and other relevant bits of physics and so on. And we can additionally instruct a computer just to assume that the universe has these materials that we believe to be there. So we can tell it, we think the universe is made up of such and such materials, including something like dark matter, which is there. It is, because there's a lot of it, it's going to pull stuff around through gravity, but it's not actually going to be directly visible. And then you can tell the computer something about how you believe the universe started, and we have some very good evidence that the universe, for example, is expanding. So it was once very small, around 13.8 billion years ago. Everything that we know today would, in fact, have been microscopic. And you can tell a computer all of these things. And to cut a long story short, you can then perform your simulation and see what happens. Now, the real beauty of doing this is that you get to see this mini universe inside a computer in whatever way you want. So if you want to see what dark matter is doing, even though dark matter is invisible in the real universe, you can, of course, instruct the computer to show you what the dark matter in the virtual universe is up to. And let me show you from one of my own simulations what this looks like. So I'm going to show you time evolving. At the moment, the universe is a microscopic dot in the center of the screen. And as time starts, the Big Bang happens. The universe is expanding. This is, in fact, just a small segment of what we believe to be the true extent of the universe. But as well as expanding, you'll see another thing happening. You'll see these kind of green lines of structure start to form. Now, the green is a color I've chosen. Green is not a color that comes up in astronomy very often. This is, in fact, representing the dark matter. And what the dark matter is doing is, just because of its huge gravitational pull, it is creating structures almost spontaneously from tiny little quantum ripples at the beginning of time. And it's creating these structures, and because of the particular way that gravity pulls things together, those structures start to look first like sheets and then like filaments, and they leave behind them huge empty voids, and it generates this cosmic web that appears to be out there and that we're trying to study more with things like Euclid. But of course, you would not be able to see this if you lived inside this universe. You would not be able to see this because this is dark matter. So we tried to get the computer to predict what would this universe actually look like if you were able to put a telescope inside this virtual universe. And here it is. It is tracing the same cosmic web, but the dark matter has done all of the work here, actually. The dark matter has created all of those structures, and then the stuff that you actually see is kind of tracing it out. So I can take a fly through this universe now, and you can have a look up close what these things look like. These things that look like tiny dots of light are actually little forming mini galaxies. We're quite early on in the history of the universe here, about 1.7 billion years into the history of the universe. And if I switch back on the dark matter, you can see that there's a kind of scaffolding there. The dark matter is providing a kind of scaffolding to build these galaxies. And then what happens next is, if I start evolving through time again, as the years tick by, the little mini galaxies that form in the early universe start falling down this scaffolding and building bigger and bigger galaxies. And this is going on throughout the universe. Lots of little mini galaxies coming together, building things that are larger and larger. And if you fast forward through the rest of cosmic time, eventually you end up with a big swirling mass of stars and gas, or in fact many of these things. But of course, digitally, we can fly into this thing and go and take a look at what would this look like if we lived in roughly the place inside a galaxy where we believe we reside, our sun and planet Earth. And it looks not too bad. It looks a bit like the night sky. And so we think we're onto something here. But this has prompted people to make that leap, to say, well, we are doing so well at recreating reality. So imagine that some far future evolution of humans, with some far future evolution of technology, continue this kind of activity of recreating something like the universe inside computers. Eventually, surely we'll have plenty of detail inside those, and you could imagine, you'll form planets, and on those planets you might get life evolving, and intelligent life might even emerge on these planets. And then it's a small leap from there to say, well, maybe we are already inside a simulation conducted by some far future version of ourselves. There's nothing that immediately seems to rule that out, and so people have got very interested in this idea. However, I think it's wrong. I think we're taking too big a leap here. And the way to see that is just to look at the numbers. So the virtual reality that I've shown you, the best we can do, it uses about 10 to the 14 bits of information. It turns out that we can use physics to estimate the number of bits of information that it takes to describe and process our universe as a whole, and that number is quite a lot bigger. It's 10 to the 124, and it's not bits, it's qubits. So you have to do this on a quantum computer, not on a classical computer. Quantum computers that are capable of doing this are clearly a long way off. Nonetheless, some people have speculated that maybe it's just a matter of time. And so, if you look to some of our greatest thinkers, our greatest philosophers, our greatest guides to life, people like Elon Musk, then you'll find them making some pretty strong statements, like this one. Games will become indistinguishable from reality, so he's approaching it from the side of computer games, but same basic idea. It would seem to follow that the odds that we're in base reality, that is, a reality that isn't actually a simulation, is 1 in billions. Now, you might be skeptical about Elon Musk, I don't know, that's a personal preference that you may or may not have, but perhaps a slightly more surprising person who's picked up on this, that you wouldn't expect so much, is Richard Dawkins. So Richard Dawkins, famed atheist and a promoter of rational thinking, has said, I conclude that we could very probably be part of a simulation by future humans. Now, I don't reach that conclusion, and the reason is this. If you wanted a computer that could really process 10 to the 124 qubits, then you can figure out how much energy that would take. And in fact, it's the reverse of the simulation it's the reverse of the calculation that got us to 10 to the 124 qubits in the first place. You go backwards and you say, well, how much stuff would I need to leverage to process 10 to the 124 qubits? The answer is I would need to use the whole universe to simulate the universe. And so this is an incredible, incredible nonsense. But I think it's not just, thank you. It's not just a nonsense. It's a kind of dangerous nonsense. Because if you look at the state of politics and public discourse, where truth is under fire and science is under fire and rationalism is under fire, I think we have to be really careful about how we treat these ideas. It can seem like a bit of fun, but I think they actually dovetail into a kind of post-truth politics, and I think there's a serious point here that these are not just games that we're playing. We shouldn't be talking about these things unless we're absolutely sure, and I would say it is too much of a leap to say that we're inside a simulation. So, if you've enjoyed that, if you like those ideas, if you'd like to read more about how this ties into multiverses and AI and goodness knows all what, then there's a really fantastic book out. And I will leave it there. Thank you so much.
Thank you for that. That was super fascinating. I have so many questions, but so little time. So I'll limit myself. First of all, this is actually the second time this year that I've listened to a presentation talking about the fact that only 5% of the known universe is observable, right? So if only, and that 5% is ginormous in terms of that 5% of observable is already the scale that you obviously talked about it's basically beyond human comprehension or normal. So how do we actually know that this other 95% exists? Where does that actually come from?
Well, it's come from a long period of work. Some of the first hints were just looking at galaxies, seeing how they behave, in particular looking at the stars on their peripheries, which are moving round the kind of outskirts of the galaxies really fast. And if you imagine taking a corner in your car too fast, you would just expect to skate off the road.
Yeah.
So when you look at these galaxies and their stars taking those corners super fast, you ask, where's the force coming from that keeps them going round? And the answer is you can't make sense of it unless there's some extra stuff producing an extra gravitational force. And that's where the idea came from. But it then developed much further than that, to a large extent through the work of simulations. For example, the prediction of this cosmic web. And the fact is that we do now know it's out there. We can pinpoint its properties pretty well, even though we're going to do even better with something like Euclid. So dark matter makes that very distinctive prediction, which then turns out to be correct. Okay. So that's a very short version of what the evidence is.
Yeah, I'm sure there's a bit more to it, but that is, thank you for that.
Yeah.
So getting on to so I actually didn't realize Richard Dawkins had said that. And why does he talk about this being probably a simulation by future humans?
Yeah, so a lot of this came out of the work of philosopher Nick Bostrom.
Yeah.
So Nick Bostrom is actually very careful about what he says, if you go and read what he's written about this. But then people have picked it up and run with it. But Nick Bostrom's scenario is very much about future humans. So it's the extrapolation of Moore's law, to the idea that if you just follow Moore's law for long enough, you will get the kind of compute abilities to perform what Nick Bostrom calls ancestor simulations. So his idea is that we would be trying to simulate the evolution of life and the emergence of intelligent life in particular. So he frames it very much as humanity doing this. And then sort of simulating itself. It doesn't have to be that, but that's the thing that Nick Bostrom wrote about, and therefore the thing that Richard Dawkins is picking up on.
Okay, cool. The final thing that struck me is that if we are, so let's say there is this future human Elon Musk out there that in his spare time has simulated us and everything that we're experiencing.
I think you should fix Twitter first.
I'll send that to customer service. But it just seems to me that ultimately, so if this is true, that there's obviously nothing we can do about it. But I actually thought let's assume it's not true, taking your argument, that actually entertaining the thought is it serves no purpose as far as I can tell. There's nothing pro-social at a personal level or at a societal level as to believing this might lead us to.
Yeah. So I mean, these kind of ideas that we live in some kind of fake reality can be traced, way back. So famously, somebody like Descartes talked a lot about this, but much further back than that to early Christianity and the ideas around Gnosticism and the fact that we are entrapped in a fake reality, and all the way back to Plato. And so it has been a rich philosophical line of inquiry, but generally it doesn't lead you very far in terms of how you should live your life or how you should do science. And if anything, it leads you towards nihilism. And there is actually a film out there called Enter the Matrix, I think it's called, interviewing people who actually believe in the simulation hypothesis and looking at the life decisions they've made around that. And it's led to some actual very, very real human tragedy. So I think, if anything, it leads you down a tragic path. But I suppose even if you believe it, I would say it shouldn't really have an effect on how you live your life. But nonetheless, it does for some people.
Interesting. Andrew, thank you so much.
Thank you.